Hello, my name is Will Brewer, and I am an HVAC application engineer with ABB. In this video, I will cover some basics of cooling towers and the features available with the ACH580 series of drives and integrating controls for cooling tower applications. For this video, I want to start by reviewing the analog and digital I/O available with the drive and applicable for cooling tower programming. Then I'd like to step through different system types for cooling towers, their components, and basic functions. Then we'll review several of the drive features available for integrating cooling tower control into the drive. Next, I'd like to present the idea of multi-cell fan control with an intelligent drive programming. Finally, we'll review some other HVACR applications. Here we have a basic cooling tower setup for the default I/O available with the drive. We will wire a temperature feedback source into AI2 to control the fan speed to temperature feedback. We have a start-stop signal to enable the drive, a vibration switch start interlock for a safety shutdown. We will program a fixed temperature set point into the drive, or this can be adjustable from a building automation system over a communication protocol. And finally, we have a run status output and a fault status output that can be used for monitoring. If additional I/O is required for your application, several different extension modules are available for the 580 series of drives. There is only one slot available per drive, so only one extension module can be used at one time. Now let's take a look at a couple different cooling tower system types, their basic components, and their functions. Of the numerous types of cooling tower system designs, I'd like to review two commonly used with HVACR applications. The first is the open loop cooling tower, which passes warm condenser loop water over the top of the tower media, and that falls to the cold water basin before returning to the condenser loop. The cooling tower fan draws in outdoor ambient air over the water media and removes warm, moist air out of the tower, removing heat from the condenser loop. These types of towers are most common, typically have smaller footprints, but require more water usage and water treatment over time. The second type of cooling tower is the fluid cooler, dry cooler, or a closed loop cooling tower system. In these designs, a heat exchanger is used for the condenser loop, preventing the outdoor air from being exposed to the condenser water. These types of towers include a spray pump that recirculates cold basin water to the top of the heat exchanger to spray down for evaporative cooling. These types of towers typically have a greater first cost, maybe larger footprint, but have a lower cost over time due to reduced maintenance requirements and water treatment. In this system configuration, warm condenser loop water enters the tower, passes through the heat exchanger, and returns to the condenser loop. The tower fan draws in dry, outdoor air up through the tower and rejects warm, moist air out the top. With a variable frequency drive controlling the tower fan, we can maintain a more stable tower leaving temperature set point, reduce the amount of water consumed through evaporation, and significantly reduce the energy required to turn the fan. Fans coupled to motors can be connected either through a gearbox, directly driven from the shaft of the motor, or traditionally through a belt and pulley system. At the bottom of a cooling tower, the water basin is where chiller condenser water leaves the tower and returns to the supply loop for open loop cooling towers. For fluid coolers, the spray pump will draw from the basin to spray nozzles above the heat exchanger for evaporative cooling. For proper operation, the basin water level must be maintained. The water level will be measured with either a float or a level sensor. This can be used to open up a makeup water valve to replace water evaporated, enable a spray pump, or a basin heater for cold climates. Evaporation of water is an efficient transfer of heat from the condenser loop over the heat exchanger. However, this increases water consumption as a trade-off to higher energy usage of the tower fan and motor running at full speed. Water lost through evaporation is replaced through a makeup water valve at the water basin. Water level monitoring with a mechanical float can open up a valve as needed. Or a level sensor can be used to monitor and control when to activate the makeup water valve. Solids also build up in the tower basin over time from sediments in the water after evaporation, known as blowdown. These will need to be periodically drained and replaced with fresh or treated water. In colder climates, fall, spring, or even winter operation, the outdoor air conditions may be such that the basin water will be able to freeze. This is possible when the system may be at partial load, if loop flow has slowed down, or the system is shut off or in standby overnight. The basin heater can be locally controlled with its own thermostat, or enabled from a controller output monitoring the basin or loop temperature. A separate power source is required for the electric heating element. For fluid coolers, the spray pump is enabled for wet or evaporative cooling and recirculates basin water up over the closed loop heat exchanger. In a hybrid system, dry or wet mode can be enabled first, with the other being secondary cooling. Wet mode cooling is more efficient, with evaporation removing more heat but consumes more water that must be replaced. While dry cooling isn't as efficient and consumes less water from no evaporation, it does require more electrical energy. This may be desired for part load conditions or depending on local utility rates for water or electricity. To optimize the cooling tower heat rejection and maintain a stable condenser loop set point, a temperature sensor in the water loop, or basin for open loop towers, can be used as feedback to modulate the fan speed or enable the spray pump. This feedback with PID loop control will modulate the cooling tower fan or stage another tower cell on or off to reduce energy, saving significant cost over the life of the tower. Common safety devices for cooling towers are a vibration switch that detects an imbalance in the fan and can shut down the VFD run command to protect the tower from being damaged. Start interlocks will provide warning messages to indicate the reason the fan is not running to quickly diagnose the issue and perform repairs. Now let's take a look at a couple drive programming features useful for these cooling tower applications. If integrated with a building automation system, tower fan speed could be controlled by the BAS based on loop temperature feedback. Drive start-stop speed and status could be hardwired or over network communications to the BAS. Alternatively, the temperature feedback can be connected directly to the tower fan drive and an internal process PID loop used to control the fan speed to maintain temperature set point. A fixed set point could be used or adjustable and sent from the BAS. The PID gains are adjustable to tune tower fan response time to loop temperature changes. A sleep function can be used to turn off the fan during low loads when the temperature set point is met or only evaporative or wet cooling is required. A wake setting can then be used from sleep and turn the fan back on before the loop is at or going above temperature set point. Now let's take a look at programming the drive for process PID control. I'm going to select Menu to get to the primary settings. From here, scroll down to PID control and select. I'm going to manually select Use PID control, which will set the active PID to always active. And that's great. I want to be continuously monitoring the loop temperature feedback for the PID. For start, stop, and direction, you would typically just select DI1 for start, stop. In my case, I'm going to select it with DI2 for direction for use later. Other options available are embedded field bus control from a building automation system, or your other digital inputs, maybe timed functions. Then I click Save. For units, I'm going to leave it in degrees Fahrenheit. For feedback, I'm going to select this to get to my feedback source AI2 is the default, and that's great. That matches my wiring diagram. I need to get into the AI2 scaling. 0 to 10 volts is fine. I need to adjust the min and max range though to match my sensor. I have a 20 degree to 120 degree immersion temperature sensor for 0 to 10 volts. That's now going to read about 70.6 degrees. That looks right. For my set point, I have the choices to do constant set point or change my set point source. I'm going to go ahead and leave it at a constant set point and adjust it here. For tuning, we'll leave tuning at the defaults for now because this is just a demo unit. That is where you would adjust it in a real life situation. For increased output, I wanted to increase the speed of the fan when the feedback gets greater than the set point. For the sleep function, I want to enable, so that way when the fan speed gets to the minimum after a delay of 60 seconds, the fan will shut off if the PID determines that the loop temperature is satisfied without the fan. Here for wake-up deviation, I actually want to set this to 2 degrees below the set point. When the feedback gets to 83 degrees and above, it'll turn the fan back on and enable it to catch up to the increasing loop temperature set point. At a negative 2 degrees from the sleep function and the set point, we have about a 2 degree dead band as well, where it'll either stay awake and run or stay asleep if coming down. That should be it for the PID control. Enabling system components or making decisions based on feedback can be handled by a supervision function. Using the hybrid tower example, Supervision 1 will be for enabling the spray pump. In a dry cooling with wet trim application, this will leave the set point set to 2 degrees above the tower fan process PID set point. Or for wet cooling with dry trim, enabling the spray pump at loop temperature and adjusting the process PID to be 2 degrees above the spray pump. If basin heating is required, Supervision 2 can be set up to enable the basin heater when the basin water temperature drops below 40 degrees Fahrenheit and remain enabled until the basin temperature rises above 45 degrees Fahrenheit. For the supervision function, I'm going to set up the spray pump output to enable based on the basin temperature feedback. For that, in our wiring diagram, we had a 0 to 10 volt signal into AI1. So let's start by going into the menu, selecting the I/O, scroll down to analog input 1. Here we need to adjust the 0 to 10 volt signal to match our temperature sensor. Let's use the same example we had for the process PID loop using a 20 degree Fahrenheit to a 120 degree Fahrenheit sensor. Now we can double check that the range matches what we would expect for a signal and loop temperature set point. So here at about 85 degrees, I'm going to be at about 6.5 volts. Now, back in the menu to primary settings. To get to supervision, we go down to advanced functions. Here we enter the supervision menu. We have 3 supervisors available we can set up here. Let's select Supervision 1. The first option is to enable the supervision based on low set point, high set point, or both. For the spray pump, we want to enable when the feedback is above a set point, so we will select high. For action, we can either have a warning that the supervision is active, we can fault and stop the motor, or we can take no action. For signal, we want to use AI1 that we set up in the I/O menu, and then for the high limit, we need to use the analog input voltage value that matches the temperature feedback we're looking for, which was about 6.5 volts for 85 degrees Fahrenheit. To prevent short cycling the spray pump when the feedback temperature is at the supervision set point. We'll add a ½ degree plus or minus deadband to the set point. We'll use the hysteresis setting here to add 0.1 volts, which will be equal to 1 degree Fahrenheit. And the hysteresis function adds half above and half below of that value to our high limit. So now the spray pump will remain enabled until 85.5 degrees, and then as the temperature comes down, not shut off until 84.5 degrees. Now let's set up Supervision 2 for the basin heater. For the function of this supervision, we're going to use the low limit. The both function enables the output of the supervision above the high limit and below the low limit, but we want to have the basin heater enabled below a threshold and remain enabled with a hysteresis above that low limit. For the action on this supervision, we will use warning to show on the keypad that the basin heater is enabled. Again, we will use the AI1 voltage feedback for the basin heater. For our low limit, we want to measure the temperature of the basin at 42.5 degrees Fahrenheit, which is equivalent to 2¼ volts on our temperature sensor. Then, with a hysteresis of 5 degrees, which is 1/2 volt on the temperature sensor, we will enable at 2½ degrees beyond the low limit. So 2½ degrees from 42.5 degrees will be 40 degrees Fahrenheit. And it'll remain enabled until 2½ degrees above the set point, which will equal 45 degrees. For the warning label, we will show Supervision 2 is enabled. And then for the instruction line 1, I have shown that it'll read the basin heater is active. Here in the settings, you can even preview to see what it'll look like. So in this example, Supervision 2 will be enabled, showing that the basin heater is active because the temperature sensor has registered below the low limit set point within the hysteresis. Since the cooling tower fan and motor are located outside, outdoor air conditions can cause condensation to build up within a motor, causing premature failures. It is common to install a motor heater to help mitigate the condensation buildup, but this requires additional components, wiring, and electrical load considerations for the tower. The drive features a motor preheating function and passes a small amount of current through to the motor windings to generate heat uniformly around the motor. This electrical load is already considered with the drive power requirements and requires no separate heater or wiring. To enable motor preheating, there are 2 menus available to access the settings. The first is primary settings, but in this menu you can only select when to activate preheating and what percentage of current. Instead, I'm going to go into parameters, the complete list, down to group 21 to select the motor preheating options. Here you can select the input source of on, physical inputs, supervision points, timed functions. You can adjust the time delay for when the heating will activate after the motor stops. Again, the percent current, and then at the bottom of the list, the preheating unit selection. So we will keep it in power, and then to enable the drive to provide an adjustable amount of kilowatts to the motor for heating. Here we'll select 100 watts for a common amount of motor heating. Select save, scroll up to enable motor heating, which you cannot adjust the power amounts while it's enabled, and activate it. When the motor heating is activated, a warning message will be displayed on the keypad indicating that it is active, as well as an icon will show up by the drive name. You can hide this screen to continue making adjustments. In cold climates or winter operation, ice buildup may form on the outside of the air intakes. If no bypass valve is included to direct water flow to the basin or dampers to close the air intake louvers, reversing the fan direction can move warm air back out to the louvers to melt ice before returning to normal tower operation. Tower fans without a variable frequency drive won't be capable of this reverse direction option, requiring the other forms of ice prevention. To program the drive for reverse operation to do de-icing in the cooling tower, we're going to again go into Menu, look at Primary Settings. Now in the Start-Stop Reference section, we're going to scroll down to the Start Auto Location. This is already set to DI1 Start-Stop and DI2 Direction from when we set up the process PID. But to enable the direction to reverse the operation of forwards and backwards of the fan, we need to get to another option available in Parameters and the Complete List. Here we'll go down to Start-Stop Direction. This is where in Start and Into are enabling the direction change. But we need to allow the drive to do a request for reverse direction. With this enabled, DI1 will start and stop the fan, separate from DI2 enabling forward direction or reverse direction. Scheduling the start, stop, seasons, or rotation can be set up with timer functions within the drive. For cooling towers, a summer and winter season could be programmed to change the process PID set points. In a multi-cell system, which tower is enabled first could be scheduled to rotate on a weekly basis. Shutting down operation overnight or standby if a chiller or condenser doesn't require 24-hour operation. Or switching between dry and wet mode based on on-peak or off-peak electrical rates. To enable the timer functions for use in changing applications, scheduling standby modes, rotation and multi-drive setups, you can find them in the primary settings and advanced functions. In this quick example, I'm just going to set up one timer to be used for starting the drive and or PID. Boost time can be used for a manual activation. I won't cover that. For timer 1, I'm going to set up the start time to be 6 a.m. I'm going to set up the duration to be 12 hours, 6 a.m. to 6 p.m. So here you can do 24 hours a day, and then days, hours, and minutes of duration. For active days, you can do every day of the week, only weekdays, weekends, or individual days of the week. This can be useful for setting up the drive timer function to activate a rotation at a single day of the week. To use the time functions, you will need to set up the clock and date time settings of the drive. That can be found by just going back from time functions, advanced settings, down to clock, region, and display, from here down to date and time. You can manually enter and adjust these values if they're not already set or reasonable in the drive, and they will sync from a laptop connection as well over USB if you are using the Drive Composer software. If more complex programming is required beyond the standard features of the drive, adaptive programming is available with the software tool Drive Composer. See the video description below for links to download this software as another video that covers the programming tools and an application example. Now let's cover the topic of multi-cell towers integrated with an intelligent drive control. The ABB ACH580 series of drives includes a multi-pump and fan feature called Intelligent Pump Control. Don't let the name scare you away from the idea. This multi-drive communication function is just as capable for fans as well as pumps. With process PID control, Multiple cooling tower fans can be staged and modulated to meet system loop demand. In summer conditions, the tower fans can shut off if demand is low, or can be staged on at a reduced speed to meet demand and use less energy. In winter conditions, all fans can be required to prevent ice buildup while controlling fan speed to meet loop setpoint. IPC settings allow adjustment of start and stop speeds of the master drive and follower drives. A lead lag setup and rotation of the master and followers or standby fans can all be selected and configured. Now let's get into enabling intelligent pump control within the drives for this multi-cell fan application. Again, we're going to go to Primary Settings and scroll down to Pump Features. We want to get to multi-pump control for this multi-fan application. The mode will be IPC. Our first drive will be node number 1. The communication between the drives is over our I2I configuration. You can either use the embedded field bus terminals or an external field bus adapter if you would like to use the embedded field bus for one of the native protocols. Now, the settings for this pump will be the ability to name the drive. If you have 3 drives all next to each other with the same name, it'll be difficult to know which one's which. So I'm just going to add a designation to each to show which drive I'm looking at. My first drive will be node number 1. All of my drives will be able to be master, so that the rotation between drives, either in a lead lag setup or in the evenware application, each drive can take over function from another. If you're using the evenware feature, you can determine which tower fan you would like to run more often or less often. In this programming, we're just going to leave it at medium, so each drive and fan are equal. Now back to shared settings. These settings apply to each drive in the grouping and can be synchronized, so only one drive has to be modified, and we'll pass that setting on to each drive. Here we would tell all drives how many are available in the grouping for a max of up to 8 drives for the IPC logic. Here we can determine if we need to have a minimum number of tower fans running. In this case, we'll leave it as always run at least 1 fan. If you have an application in a cold climate or winter, and you want to always have every fan running at the minimum speed, you can require this to be equal to all the towers. You can also use time functions and the adaptive programming logic to have that be set up using the timed function and automatically switch between 1 and 3 fans. If you wanted to have a lead lag standby rotation, you could limit the number of tower fans to run down to 2. If only 2 towers are needed to meet your demand, and you always want to have 1 in standby, you can limit that. In this example, I'll leave it at 3 so I can have the total number of towers running. For start-stop speeds, I want to start each fan at or near the minimum of the fan, so that way my fans will come on at minimum speed for each cell before I ramp up. This may reduce the total amount of energy required, since each fan running at a lower speed will require less energy than one fan running at a greater speed. And then I want to stop the pump after it has been sitting at the minimum for a period of time. Next, we can take a look at the transition smoothing. This can be useful more in a pumping application where you might want to buffer out spikes or dips. Maybe it's also useful in a temperature environment if something impacts the sensor. You don't want the towers turning on and delaying if necessary. Here you can adjust the maximum amount of wear imbalance for the evenware default setting for IPC. In this case, each fan will be required to run up to 24 hours before switching to the next fan in the rotation. If we didn't want to let any fan sit for a period of time, we could require it to sit no longer than an adjustable amount before requiring it to run. And here, the default application is to use the PID control for the condenser water loop temperature. As demand in the loop increases and each fan gets above the starting frequency, another standby or follower fan will be brought on to meet the loop demand. If there are more settings that you would like to implement, such as a timed rotation instead of even wear, Group 76 in the complete parameter list is the multi-pump configuration. Here you can also see status of the IPC logic, access to the node numbers and communications, the minimum and maximum number of motors allowed to run, the starting and stopping frequencies, acceleration smoothing to help out with the tuning of the system, and here's the auto change. So here we'll change this to timed function 2 that we have not set up yet. Here we could now set up time function 2 to enable once a week for a certain period of time. That will trigger each drive to switch who is the master. Here's our auto change imbalance settings and the priority. Here is a summary of the menus and parameter groups we use to set up the drive as the main controller for the cooling tower application. Adaptive programming available with the Drive Composer software can be leveraged to implement more complex logic-based decisions needed and is similar to what is commonly found in commercial building automation systems. Also, here are the QR code links to a couple of the ABB tech notes referenced, as well as links in the description below. Now that we have reviewed only several of any possible cooling tower configurations using the drive as the main controller, here are some of many other HVACR examples using standard programming, drive extension modules, PID loops, or adaptive programming. So in review, we briefly covered typical variable frequency drive I/O connections for cooling tower applications. We took a look at a few cooling tower system types, their standard equipment and functions. We stepped through the programming features available with the ABB ACH580 drive, ideal for controlling different cooling tower applications and functions. Finally, we explored the possibility of using an intelligent drive control feature to manage a multi-cell cooling tower application standalone from a building automation system. If you have any further questions, please reach out to your local ABB representative. Thank you for watching.